or unmute yourself and say, yeah. Yeah. Well, I think, yeah, we're at 10 o'clock. Yeah.
Good.
Hi, welcome. Welcome, everybody. Thank you for being here. My name is Jeremy Stelzafus. I'll take the opportunity to introduce Taryn here real quick. This is so special to be here today to celebrate Taryn's work. So Taryn Contento, I'm sure you all know because you're here. A little background, well, a quick structure of the day real quick. So Taryn's going to give us a presentation on her fabulous work, and we will have the opportunity afterwards to ask questions after she's done. And then after that sort of question and answer period, folks online too, if you have questions, feel free to put them into the chat. We have a moderator here who can read your questions to us at that appropriate time. And then after that question and answer, we'll kick you all out and we'll have a meeting just with Taryn and her committee. Quick background on Taryn. She provided me some details on her background before I knew her. So in undergrad, Taryn was really interested in sustainable agriculture. And what I thought was really cool, she was also the director, if I get this right, of the University of Arizona Community Garden. And I don't know what your undergrad looked like. I wasn't the director of anything. So just a great example of Taryn's leadership qualities and skills, which we've all seen exhibited in her time here as well. She worked for 5 field seasons in the Great Basin, Sierra Nevada, and Western Colorado with the Forest Service, BLM, and the Nevada Department of Wildlife. And then since she's been here, she's been just a true leader in our department, Forest and Range and Stewardship, in the graduate degree program in Ecology. She's an officer in the Society of Ecological Restoration Student Club. She helped our department increase our diversity, equity, and inclusion materials in various classes last year, which we're all thankful for. And she's now the Science Communication Chair for GDPE, all things that she excels at, and I'm so proud of her for. With that, I'll turn it over to you. Again, thanks everyone for being here.
Thank you all for joining me for my master's thesis defense entitled Willow Growth Response to Altered Disturbance Regimes in Rocky Mountain National Park. I'm going to start by talking about my background, how I got here today, and ultimately where I want to go after my graduate school experience. I started out work at the University of Arizona. I graduated with a degree in sustainable plant systems, which Jeremy mentioned. I then went on to do field work, pivoting from horticulture, and then quickly realized that I really enjoyed those experiences, but ultimately I wanted to know, where did those research questions come from that had me gathering that field data? And then where did that data go, and how do people interpret it later? So I wanted to pursue graduate school, which you see on the far right here. And then ultimately in the future, what I want to do is science communication and connect my love for natural resources with my research. So today I'm hoping to explain to you my research project, but ultimately I want you guys to have a larger context for where this research falls and why it's important. So I'm going to start by taking a deep breath and then talking about the background of this project in the context of why you should care, which is ultimately riparian areas, their functions, and the roles that disturbance play in them. And then I'm going to talk about the human use that has modified those landscapes, and then how land management agencies are approaching those modifications today. Then I'm going to introduce my research questions and talk about the methods and data collection I use to collect data to answer those questions. Then I'm going to talk about the results and discussion and give you a little bit more nuance around the answers to those questions. And then finally talk about the management implications that come from the conclusions I drew based on the data. So I'm going to start by giving you guys background, and I want to point out here on the bottom I have a progress bar. So at any time you get lost, just refer back to that. So just so you know, when I'm talking about this background about riparian areas, I want you to understand where we're going with this. So why am I talking about riparian areas and their functions? So my research questions, just quickly, are what are the impacts of altered disturbance regimes that include increased herbivory, altered hydrology, hay production on willow height, cover, and annual growth? So most importantly, what is a riparian area? Well, basically, it's an interface between terrestrial and aquatic systems, which means it has attributes of both. So it has soils and plants and animals adapted to high water levels and also high levels of disturbance. And what that leads to is really highly productive heterogeneous landscapes. So how do these areas become so highly productive, and why are they so important? That's in part because of disturbance regimes that occur in these areas. And disturbance regimes are really just a pattern of disturbances that occur in a landscape over a period of time. And when I talk about disturbance regimes, I'm talking about things like floods that would occur every spring as a result of snowmelt. Talking about beaver dams that would cause ponding and spreading of water across the landscape. And I'm talking about herbivory, which would naturally occur from things like elk, deer, and moose. And then the function of really those disturbance regimes, I mentioned they're really important to riparian areas, is that they provide inputs into the system. So they're highly productive systems as a result of these inputs that are coming from other areas. So you can think of things like floods, which would bring water, but also deposit sediment and nutrients and debris in riparian areas during floods. So do note the color of the examples of disturbances, because I'm going to mention them when I'm talking about what a functioning riparian area would look like. So you'd have riparian vegetation, and when I'm talking about riparian vegetation, I'm generally talking about woody species that include things like alders, willows, cottonwoods, and aspen. And that riparian vegetation, like I mentioned, is adapted to high levels of water or periods of high water, so that can be attributed to flooding and beaver dams. So those disturbance regimes lead to these attributes in riparian systems. You'd also have animal life that's feeding on this highly productive vegetation. That represents herbivory, but that is usually managed by things like predators, seen here. Other animals exist in these systems, such as beavers that would build beaver dams. You also have sprawling channels, which are also the result of the disturbance caused by beavers. You'd also have this ponding that from backed up water. And then you'd have, because of this abundant riparian vegetation, you'd have shade on the streams. And you have stream channels that are connected to floodplains. So floodplains are the adjacent area to the stream. And that'd be caused by beaver dams and flooding again. So a lot of the hydrology attributes come from beaver dams and flooding. So then now that you know the attributes of riparian areas, what functions come from those attributes? And so riparian vegetation, like I mentioned, I'm going to specifically talk about willows because they're a huge component of riparian areas. But willows would slow water. Riparian areas in general filtrate pollutants. Because riparian vegetation is along stream banks, their roots would stabilize the stream banks and prevent against erosion. You have water retention over a longer period of time because of the ponding caused by beaver dams. You have abundant habitat from both the debris flows as a result of floods and also because of riparian vegetation, such as willows. And then you have that moderation of stream temperature that's caused from the shading of riparian vegetation, which is really important for fish species. So because these areas are really productive and because they have a lot of access to resources, obviously they're going to be appealing to humans. And when we originally settled in the Western United States, we chose riparian areas as our location. So how did humans then modify these landscapes after they arrived on them? Well, you can see that in terms of agriculture, which would result in things like clearing of riparian vegetation and water diversions. So this is supposed to represent the clearing, and that would be hay production. We would also do things like damming, both for use in agriculture, but also for hydroelectric power, for use over a period of time. And then because these are in low valleys and they have great access to resources, we put our houses there, again, clear vegetation and modify this landscape. And then we'd also alter the animal species that we see. So we would kill certain species to eat certain species that alter what you normally see in this landscape. So then what were the results of this modification of these landscapes? Where this general riparian use led to these altered disturbance regimes. So alteration of flooding and when it occurred, diverting water and damming would decrease the amount of water in floods. Clearing vegetation would decrease the beaver dams because beavers need riparian vegetation to build their dams. And then altering animal species would lead to something like increasing herbivory because there's more of certain species and less of other species. And generally, this leads to this loss of riparian function that I mentioned, all the things that come from these specific attributes of riparian areas. So then we see this historic change between how we thought of riparian areas historically as this commodity or something to be used, and sometimes really not seen it valuable at all, to this more current view where we see riparian areas as an integral part of ecosystems for the reasons that I mentioned, the functionality that they provide. So because that was a lot of information and not a lot of people may have heard it, just want to clarify the disturbance regimes provide riparian areas with ecosystem function, in part. Human modifications of riparian areas has led to the alteration of disturbance regimes and the degradation of riparian areas in general. And then the realization of the importance of riparian areas has led to this change in mindset around land management agencies, land management use for protecting and restoring them. So I'm going to talk about my research in particular. This research was done in Rocky Mountain National Park in the Comanche Valley. Specifically, this is the west side of the Continental Divide, which is this raised area you see here. And it also is the headwaters of the Colorado River. So the Comanche Valley is a really ideal location to study the impacts of altered disturbance regimes because this area experienced multiple altered disturbance regimes historically. So I'm going to just give you a breakdown of what I'm going to talk about. We have altered hydrology that occurred in the Comanche Valley as a result of Grand Ditch and also from the loss of beavers. We also have altered levels of herbivory, which are the results of loss of predation and predators, and the introduction of non-native moose, as well as a history of ranching and meat production in this area. To start off, I'm going to talk about the altered hydrology caused on the landscape level by the Grand Ditch. The Grand Ditch is a trans-basin water diversion, which diverts water from the western side of the Continental Divide to the eastern side, so where there's more precipitation but less people, to the area where there's more people and less precipitation. It's 14 miles long, and it diverts around 50% of the tributary water that would normally enter into the Colorado River and ultimately the Comanche Valley. And this is a hydrograph, so on the x-axis here you see time, the y-axis you see discharge or volume of water. And I want to exemplify here that before you have these water diversions, you have a higher level of water volume versus now because of that diversion of water, which leads to a decrease in sediment deposition and nutrient deposition and all those attributes to floods that I mentioned earlier. Another alteration of hydrology in this area that's a little more localized is caused by the loss of beaver. And the loss of beaver was a result of generally occurring across the West where people killed beaver for use in fashion fur that was used in Europe at the time around the 1800s. And also because they were seen as a nuisance animal, right? They cause damming and diversions, and if you're a farmer, you don't want that. So they were eradicated in the Comanche Valley. And you see here on the left, this would be a functioning system that had a beaver. It has a dam across the stream. It raises the water levels. But as you see on the right here, this is really the result of the loss of beaver. So you have the simplification of channels, you have incision, as opposed to the far right where you see kind of the sprawling water. Then we see altered levels of herbivory, and these are caused by the loss of predators. So we eradicated these, again, nuisance animals to us, so such as wolves and grizzly bears. And what that resulted in is then an increase in herbivores and increase in herbivory. So we can see that in terms of elk in the Comanche Valley when the populations increased as a result of loss of predators. We also see that in terms of moose, which I mentioned were non-native and introduced in the 1970s into Colorado. So those populations then subsequently increased and caused increased herbivory. And when I'm talking about herbivory in these circumstances, I'm talking specifically about moose and elk because they're so predominant. The other thing that occurred historically in this area to lead to altered disturbance regimes was the settlements. So people came here to settle and ranch. Most notably, probably Holdsworth Ranch. And I will note that these ranches produced hay, specifically Holdsworth Ranch into the 70s, but these other two ranches were more into like the early 1900s. And then this photo on the far right is actually in Moraine Valley, but I think it was a really awesome example of this photo taken from the 1800s, and that's hay production. So the reason that this is an ideal location to study the impacts of altered disturbance regimes is because there's a land management agency that had that change of perspective around riparian areas. So we see this manifest in the Elk and Vegetation Management Plan that was written around 14 years ago by the National Park Service in response to the realization that there was decreased willows as a result of increased elk populations. And they set goals for things like restoration and maintenance of riparian willows and then improvement of conditions for riparian willows. So as a result of this management plan, the park implemented different methodologies to increase willow growth. And those are things like simulated beaver structures, which are similar to beaver dams. You have things like exposures, which is fencing to keep out the herbivory caused by ungulates. And also lethal and non-lethal management techniques, so culling. And then all these are adaptive management techniques. So they're trying to figure out what works best and then modify their land management based on that, which is part of why this research is important. And then I did want to point out that these are what exposures look like in case you haven't seen them. So they're usually 8-foot tall fences surrounding an area. And when I talk about the exposures in this valley, there's 4 of them. 3 of them were built in the late 90s, and the other one was built in 2011. And I'll mention that again, but I want to bring that through. So because this is a priority for land management agencies, a lot of these different altered disturbance regimes have been studied before. So we see that in terms of browse and exposures. So generally agreed upon that increased browse leads to decreased growth. And then on the opposite of that, because exposures represent a low browse or excluding ungulates, that there would be an increase in growth because of exposure. There's also been research looking at altered hydrology or water levels on willow growth, and we have 3 different studies, 2 of them finding this relationship between raising water levels and increasing willow growth, as opposed to another study that did not find a relationship between increasing water levels and increasing willow growth. Other research has been done on hay production or the influence of ranching that I mentioned earlier, categorizing that as hay production. And that leads to things like increased erosion, decreased infiltration, soil compaction, and altered stream flows. So you might be asking yourself, well, why then is this study necessary if we have this prior research? Well, to start off, site-specific information, especially for the park, is really important to have that information for land management decisions. But also these problems are really ubiquitous to riparian areas across the rest, right? If we talk about Yellowstone, it's also another area where we eradicated predators and that led to increased elk. So these trends that we see with beavers and elk and how we selectively killed them has occurred across the Western United States. This is also really important. The Comanche Valley has overlapping altered disturbances. So like I mentioned, it isn't just the alteration of hydrology and the change in the water tables, but it's also increased herbivory, and it's also this impact from ranching. So these all occur at the same time. So looking at them overlapping is also a novel way to look at this research. And then finally, I mentioned that there was multiple studies with different conclusions around the relationship between water level and willow growth. And so I'm hoping to add to that research. So I want to remind you that the title of my talk is Willow Growth Response to Altered Disturbance Regimes in Rocky Mountain National Park. And then there's more specific questions that I mentioned early on, just to give you a trajectory where we're going, was what are the impacts of altered disturbance regimes, including increased herbivory, altered hydrology, and hay production on willow height, cover, and annual growth. So what were the methods that I used to collect data to answer these questions? And I want to put you guys in the thought process that I had first. The response variables I'm looking at are these growth metrics, so the height, cover, and annual growth. And then the explanatory variables are the altered disturbance regimes, so the increased herbivory, the altered water levels, and the hay production. So the response variables are responding to these altered disturbances. The first thing you need to do is identify the areas where these altered disturbance regimes occurred. So in terms of hay production, identifying the locations where historic hay production occurred. In terms of water levels, I used existing well locations. So where were those located? And then because browse was really ubiquitous across the valley, in order to have a gradient of browse levels, I used those exposures that I mentioned earlier compared to outside, which was high levels of browse. So because that was a really large view of this, I wanted to take a closer perspective so you can see on the ground what that looked like. So water levels, like I mentioned, the existing wells would be these black triangles here located in the center of some of these plots. Browse, like I mentioned, this is an exclusion. So inside of that, because again, it is excluding the impacts of browse, would represent low browse, and outside of the exclusions represent high browse. And I'll just give you a little bit of results here. The average browse inside of exposures is around 24%, and outside was around 93%. And then hay production locations were identified via aerial imagery or historic accounts of where those locations occurred. And I just outlined the areas here and then randomly selected points from within there. So data collection occurred like this. This is a hypothetical, or this is a sample plot. And inside the middle here, you'll see that if there was a well, it would be located in the center. And data was collected at a course level. So that was more of a plant level measurement of height and cover. And then a fine level measurements, plots were selected from within course level plots. This is because these took a lot longer because we measured things such as stem count, new shoot growth length, and new shoot count. And that might be abstract to you. So here is a hypothetical willow plant. I did not put all of the growth, but because I wanted you to concentrate on this far left stem. But what we do is we measure the height, which is really just the base of the plant, the tallest leader. Cover would be if you look down aerially, how much area does that plant cover? And that would be the extent of the plant. And then the annual growth metric was really a compilation of multiple attributes of a plant. So that'd be stem count, seen here being 8. New shoot count, hypothetically here is 33, but usually this is like in the hundreds, which as a result led me to do only a subset of the new shoot growth, so around 10%. And then the new shoot growth length, which would be the length of that new shoot. And then how do we collect water levels? We use those wells, like I mentioned, but they look like this. They're perforated PVC pipes in the ground. And it's important to note, because it'll come up later, after the ground surface is 0 centimeters, and as you get deeper, you get more negative in terms of where the water level is. And then in terms of how I looked at this data, I averaged each metric over the plant per plot. So height annual growth for per plant per plot, and cover was just a total amount to the extent of each plant over the plot size. So that means that there can be over 100% cover because you can have overlapping canopies of different individual plants. And how did I then compare these disturbances to the growth metrics? I used multiple and single regressions. So for the growth metrics, height, cover, and annual growth, how they compared or how they related to exposure and water level were done doing multiple regressions. But then because hay production actually didn't overlap with all of those other disturbances, so you didn't have well location in hay production sites, you didn't have exposure in hay production sites, I did a univariate regression that compared the influence of hay production on height, cover, and annual growth. So what results came from this, or how did I interpret these results in the data? I'll remind you again that my question specifically is the impacts of altered disturbance regimes, including increased herbivory, altered hydrology, and hay production on willow height, cover, and annual growth. And I'm going to give you a play-by-play of what I'm going to talk about in these results. So I'm going to talk about potentially the impacts that species played, the impacts of the exposures and subsequently browse, give you a little more nuance around the variation of browse within each exposure, because there's 4 separate exposures. And then potentially the impact of how willows were prior to excluding them and how that might play a role in willow growth variation. Talk about the impacts of water levels on willow growth, the potential threshold idea, and then the impacts of historic hay production. Then I'm going to talk about my limitations and future research that could come out of this. So in terms of species, I think this is a limitation of this study. Probably a limitation of any study that's looking at species identification under high browse, because you lose identifiable features of these species as a result of the heavy browse. So it was difficult to identify species outside of exposure. And also Salix is a genera of willows, and I'm going to refer to that now. But I knew that browse played a large role in the variation in willow growth, and so I wanted to make sure when I'm looking at the comparison between exposures and outside of exposures, species aren't playing a role. So I looked at the species composition inside, seeing here yes species in a blue box, and yes exposure, no exposure, which you'll see in pink. And these are colors we're going to use throughout, so I'll remind you of that. But what I found is that the top 3 species are the same inside and outside of exposures. And the total number of plants this represents is around 900. And the important part about this is the 3 most predominant species, Salix planifolia, Salix variana, and Salix monticola, had similar growth patterns. So they grew similarly tall and large, as opposed to, say, Salix wolfii, that is a really low growing Salix species, but only represented around 39 or 37 out of 900 plants. So I don't think that species played a large role in the variation of willow growth. And also you'll refer back to the way that I analyzed the data, which was over plant species per plot as a way to kind of standardize over the impacts that species might play. So then what are the influence of exposures and subsequently browse on willow growth? And I'll remind you that inside of exposures represented a low browse and outside of exposures represented high browse. And then I'm going to use this blue again to represent inside of exposures and this red to represent outside of exposures. And you'll see that the height is substantially taller inside of exposures versus outside. So this bottom x-axis being the absence or presence of exposure and the y-axis being height. And then this is a statistically significant relationship. So the presence or absence of exposure on height is statistically significant. My p-value of significance being 0.05, so this is substantially lower. And then the R-squared value, which is the variability in height explained by presence or absence of exposure, was also very significant. Then looking at cover, again, x-axis being presence or absence of exposure, y-axis being cover percent, and looking inside versus outside, and you see that inside in the cover is higher than outside. And again, this is statistically significant and a very high R-squared value, so the variability explained by exposures is very high. Finally, annual growth inside and outside of exposure. You see the same pattern. Annual growth is higher inside of exposures versus outside, and it's statistically significant with exposures explaining 50% of variability in annual growth. So if we look at these all together to see them side by side, again, you see that all of these growth metrics are higher. So these may conclude that growth metrics inside of the exposures are higher. And I think more importantly, that this is the most impactful altered disturbance. That is because all the growth metrics are higher, and also there's a statistically significant relationship between exposures and each growth metric. So then this is a table, a little more tangible. On the left side, you have the average of the height covering annual growth inside, outside, and under reproduction conditions. But we'll just start now talking about the average height inside and outside of exposures. So inside of exposures is 129% higher. Height and cover is 142% higher. And I like to think about this more deeply in that height and cover represents this accumulation of growth or maintained growth. So right, plants just aren't suddenly tall. Over the years, they grow and they add that growth together until they get larger. And so I'm saying that if these metrics are then taller and they have more cover, this represents that fencing allows for growth to be maintained and added on those plants, as opposed to potentially outside where you don't see as much growth. And then if we look at annual growth inside versus outside of exposures, it's 142% higher, but this represents a year to year. So this data was collected in summer of 2020. So this year it represents the growth of a singular year versus the culmination of years of growth. But if I want to make the statement then that fencing allows for the accumulation of growth on these plants, I have to consider what the plants were like prior to the exposures being built, right? So if willows currently inside of exposures were large before the exposures were built, then really I'm not saying anything. I'm just saying that the growth, the size of the plant was maintained within the exposure, which is important. But more importantly, if these plants started out small and then were allowed to grow as a result of explosion, right, then I can make that statement if they started out small. So from my research, I found that there was high browse prior to fencing. So I'm going to say that they were small prior to these exposures being built. And that is for two reasons. One is the result of natural regulation. So natural regulation was a period when these elk populations were allowed to grow larger as a result of no predators being present, but also because the park did not actively manage these populations. They were allowed to grow a lot larger than they normally would be. And that affected then the vegetation both on the east side and the west side of the park. We also see this influence again of moose that are non-native and whose populations grew after the introduction in the 1970s. And I'll remind you that the exposures were erupted in the late 90s and 2011. So the introduction of moose and their growth and population occurred before this time, which leads me to believe that these willows were browsed prior to these exposures being built. So the other thing to consider is if I'm going to call exposures low browse and outside exposures high browse, we need to consider that there's variation within each exposure, because like you just heard, they were erected in different years, but also they were under different pressures. So we see most notably that Timber Creek exposure has the most variation and the most overall browse. And that is the result of moose that were able to enter the exclosure. So during periods of high snowpack, moose could jump the fence, but after the snowpack melted, they were stuck inside the exclosure. And then they subsequently ate all of the willows that were present in there. And I do want to point out, in case you're worried, that they seemed very happy when they were in there. There was 2 moose and a cat in there in the summer of 2020 that resulted in this amount of browse. So there is variation between exclosures, but I want to point out that this section on the far right represents none, no exclosure. And as you can see here, it looks really crazy. And that is because at the top here, you have so much browse that's 100%, that all of these other individual points here are actually outliers. So there's so much browse outside that makes it look like that. So comparatively, you see that there is variation inside of exclosures in terms of how much browse there is, but relative to outside, it still represents a very low browse. Additionally, you have the reality that these 4 exposures excluded the majority of the browse for the last 10 to over 20 years. So they have that history of a less browse historically as well. So that's all those reasons I felt very comfortable connecting these all together and representing low browse. So the takeaways from the browse and exposure and their impact on its impact on willow growth is that browse is the most impactful altered disturbance regime. Also, that fencing allows for short-term and long-term growth because of the protection by fencing. So that was the cumulative growth that we see from height and cover, but also that year-to-year growth that is represented by annual growth. So then how did water levels impact willow growth? I'll remind you again that when we're talking about depth to water level, we have 0 at the surface of the ground surface, and then we get more negative as we go down. And that's going to be important because I'm going to flip the axis here. So this is 0 depth to water level. It's going to represent the ground surface. And this is going to go deeper in the soil profile. And that's again compared to height. So what we see here, and I'll mention again that this inside exposures is blue and the outside exposures is this red. The relationship between depth to water level and height is not significant, as seen here by these very high p-values. If we look at cover, again, we have depth to water level on the x-axis, and on the y-axis, we have that growth metric cover. Inside of exposures being blue, outside of exposures being red. We don't see a statistically significant relationship between depth of water level and cover. Then to look at annual growth, again, similar, we have the blue inside exposures, red outside of exposures, depth and growth, and do not see a statistically significant relationship. Although you will note that this p-value inside of the exposure with annual growth is around 0.05, so you could potentially cite a trend there in the relationship between water depth and growth and annual growth inside of exposures. But let's view these all together. The takeaways that I take, because there's no statistically significant relationship between depth to water level and any one of these growth metrics, I conclude that growth metric is not related to water level in this study. Although you might take a moment to say, Taryn, I understand that you're talking about p-values and they're statistically important, but I see trends, especially inside of exposures. It seems like when we raise water levels, we go more toward the surface towards 0. You would see a decrease in height. You'd see an increase in cover. You potentially see a decrease in annual growth. And I think that's a valid opinion to look at these trends and then consider that this is a potentially complex relationship. So if you're a land management agency or somebody that wants to raise water levels to see how it impacts willow growth, you're not going to see a conclusive result. You're not going to say raising water levels directly influences all growth metrics positively. So that makes me lead to the realization that this is a potentially complex relationship, specifically inside the exposures where you see those potential trends. So this led me to want to consider what else is happening in the literature. So I mentioned there were other studies that looked at depth to water level compared to willow growth. So these studies, I'm looking outside of my research to look at these studies. I'll point out these 2 studies by Gillieu and Marshall. They were done in Rocky Mountain area in Yellowstone National Park. And I'll note that they were experimental. So you had the exclusion of browse via fencing and also raising of water levels artificially via simulated beaver dams. What you see here is that undammed water levels were roughly around 100 centimeters, but the dammed water levels were above this 100 centimeters on average. And they did find a relationship between water level and willow growth, as opposed to these two studies, so Ziegenfuss and his unpublished data that were both done in Rocky Mountain National Park. Again, experimental, so that Ziegenfuss did excluding of browse and also raising of water levels, and had on average water levels above 100 centimeters, and also dammed and dammed and undammed. And then the other unpublished study, the average water level was again above 100 centimeters, but this was not a study where they manipulated them yet with dams or simulated beaver structures, and did not find a relationship between willow growth and water level. So that was a lot to consider, but I want to suggest that there's a potential threshold of water limitation at 100 centimeters, so 100 centimeters below the ground surface, so below which willows would be water limited. So if that was confusing, I'm going to delve a little bit deeper. These are the two studies that looked at water level as compared to willow growth experimentally and did find willow growth related to water levels. And this data is from Billy et al. On the right here, and I'll point out that on the x-axis you have the date that these water depths were taken, and then on the y-axis it is the depth to water level, and that's in meters. So we're looking at 1 meter would be 100 centimeters. The black dots represent the dam water level, so after treatment, and the white clear represent an ambient water table, so before water levels were altered. And I throw up this line which represents the threshold that I'm suggesting. You'll see that in the top two locations where they did this static collection, it seems like a pretty cut and dry relationship between water levels prior to damming and afterwards, and having them go from below to above this threshold. It's a little more complicated down here on these other two, but it made me think that it's interesting that we see some of this trend on these two plots, and that contributes to my idea of this threshold. So then what about the two studies that did not find a relationship between willow growth and water level? So I'm going to first look at the Ziegenfuss paper that was done in Rocky Mountain National Park. And this is their data on the right. And I will point out again, we have this time, so the month that the water level depth was collected. And then on the y-axis, you have depth to water level. And here is that 100 centimeter threshold. So all of the water levels were above that prior to actually undammed and dammed sites. And then this unpublished data here is again the date the water level was taken and the water level on the y-axis. And I'll point out in case you can't see it, this is -85, this is -60, and this is -60 as well. So these are all above this 100 centimeters, and these two studies did not find a relationship between raising water levels and increasing willow growth, potentially due to that threshold. So the takeaway is that in this study, willow growth does not relate to water levels. But based on other studies and looking into what their data might suggest, there could be a threshold at 100 centimeters below which willows are water limited. And I do want to note that beaver dams and flooding, so that hydrology that I mentioned earlier, really provide more than just water increases. So I'm looking at one attribute of hydrology there. So leaning toward other processes that occur as a result of these, I am not talking about that. Just water depth. So then finally, how did hay production influence willow growth? This one is very straightforward. I looked at 24 plots where historic hay production occurred, and only found 7 plots total on these plots, which decreased the total coverage below on average 1%. So if you look over here again at that table that I showed earlier, where you have the average height cover annual growth inside, outside, and under hay production conditions, you'll see that we have less than 1% cover as opposed to outside of exposures 21% and inside of exposures being 123%, so substantially lower. And I will note that I did not then compare height and annual growth across the landscape because I only had 7 plants to compare. Didn't think that really represented any trends, but we can see that there was decreased willow presence overall. The takeaways from hay production being that historic removal of vegetation leads to this current decrease in willow presence, as seen by the decreased cover and number of plants. And then there wasn't this regeneration or overall growth in these areas. So kind of these long-lasting effects of hay production. So I want to talk about the limitations of this study, right? This was observational. which meant that I was limited to locations of exposures that are already present as well as wells. And so that meant that I had a limited locations that represented low browse because there were only 4 exposures and there was no other areas that represented low browse in the valley. In terms of future research, obviously this threshold idea that I suggested is just observing the data that has looked at these relationships before. So delving deeper into that would be very interesting. Additionally, Timber Creek, because like I showed you that graph, there's more variation in overall browse comparatively to the other exposures. So it'd be really interesting to think about studying deeper the browse gradient. You're going to look at wanting to increase browse as a way to increase willow growth. What level of browse, how low do levels need to be in order to allow for willow growth? So it's interesting to think about Timber Creek as kind of maybe a low, but not completely low, and not the high level of browse we saw outside of exposures. And then it would be interesting to delve deeper into the mechanisms behind these trends. So the complex relationship that I found between water levels and willow growth, why is that the case, not just observationally? So finally, I want to talk about the management implications of these conclusions. Right, I mentioned that Rocky Mountain National Park has the elk and vegetation management plan with the goal of trying to recover willows. And they have certain goals. So they want to get to 31% willow cover. And they want to get to an average willow height of 1.1 meters. And if we look at the data that I presented earlier, the average of height and cover outside of exposures, that would be 0.5 meters of height, so below the average that they are really looking for, and then cover being 21%, and they're looking for 31%, which means to me to conclude that there is management needs in this area. So then what management implications or what management uses could then be implemented as a result of this research? Well, I did find that exposures are an effective management technique, so having more on the landscape would then be beneficial. As well, these exposures represented a decrease in browse. They represented a low browse, so decreasing browse would potentially increase willow growth. In terms of hay production, these are the areas most in need of extensive restoration because they have such a lack of willows in general. In terms of water level, does not seem to be an effective management technique to solely raise the water level based on the results of this study. But looking at the context of other studies and the results that they found, there could be a threshold which should be considered when you're considering restoration techniques and management of these areas. And then also, like I mentioned, because beaver dams and flooding and this normal hydrology that would occur on these landscapes provide other processes besides just raising water levels, maybe aiming toward those processes is a more effective management technique. Whew. So now we're at the end where I talk about how much I'm grateful for all of you. I'm going to start with Jeremy Soltkus, who's been a very patient advisor throughout this process. I want to shout out and thank you to Courtney Schultz and the whole PLPG lab who's represented here today. Specifically, Brielle Manzolillo and Katie McGrath Novak, who without I probably would be here today. Thank you to Ellen Wohl, my committee member. I want to thank Quinn, seen here with the moose in the background. She was my technician who helped me gather this data. Thank you to Rocky Mountain National Park for providing funding and also help with protocols. Specifically, Linda Zeigenfuss, who research we looked at, but also helped me along the way. I want to thank Eric Jensen, who is a R programming and ArcGIS expert and also my husband. All of my family, the friends who had to deal with me for the last 2.5 years, and then GDPE and FRS for providing additional opportunities outside of my research. So thank you, and any questions?
Oh, and if you have a question online, we have somebody looking at it. So raise your hand or type in the chat. We can hear you then. A lot of the people in this room have already seen this presentation. So.
Darren, I had a question about one of your implications was more enclosures,
Mm-hmm.
you know, to protect willows, to help them grow more. I just wonder how practical that really is, especially in a national park. And it seems like they'd have to be a pretty good size, and I would think that actually affects a lot of other parts of the system pretty negatively by keeping, or maybe not negatively, but just affects other parts of the system by keeping things out. So, I mean, what's the reality that they would use these larger, more enclosures to accomplish the goal of having taller roads?
Yeah, I think that would be a hard sell. I haven't really thought about kind of the larger implications of how it would affect these systems. I think generally because there'd be enough land for animal use without, like, otherwise. Also because they usually raise them so that smaller animals can get into use them as habitat, and they just are excluding the larger animals. And I do think it would be a hard sell because it is creating infrastructure in a national park, and also you have a public opinion of how that looks. But I think hopefully there will be enough research that supports this need, that it might be a reality just because they do have management goals for it. But yeah, it would be difficult, definitely. I think the one, so there's a lot more on the east side of the park, and the one in 2011, I think is the most recent. So I think that was the last time they did.
I think they should build wolf dens in there and put out a sign, "Well, house available."
Come on in. Yeah. Do that for beaver lodges.
We do have a question from someone on Zoom. How might existing irrigation ditches play into hay meadow restoration, if at all? Could they potentially support willow regrowth since they sort of mimic riparian areas?
Yeah, that's really interesting. So something that, if this is Jeremy Shaw, that would make sense.
Casey.
Oh, okay. Yeah, so this is something that I didn't really mention, but was visible across the landscape for these ditches that you can see in the ground. Specifically, one of the hay production sites that I looked at was very evident that they had diverted water, drained that area. I'm not sure what the use of those were. And there was in some of them like active water, but they seemed more just like dry areas. So I'm not sure. I didn't see any that seemed to mimic riparian areas like that they had active water in them. So I think it seems more like altering the topography and altering what normally would be there. So I'm not sure about that, but that's an interesting perspective. I know they are looking at that right now, so.
Cool.
Yes, Chad.
Do you have a sense that the park is looking at like climate adaptation, climate impacts and adaptation to what they might expect for future goals with willow management? And I guess I wonder how that might interact with what you found and what that might mean for them in managing.
Yeah, I definitely think that is a consideration that I didn't take into account really in this study, but I know that that is like a thought on our minds. That might be where, again, species play a role. So which species are doing best, which ones are growing under different conditions. But I didn't really address that, but I know that the park is considering that as an impact that is also impacting the riparian areas and really the whole landscape. So good question. Future research. All right. Now or never, people.
Yeah, anybody on the video?
Hey, Taryn, this is Jeremy Shaw. A great presentation. Really enjoyed looking at your work. Would you mind going back to the slide that showed the responses to water levels?
Yeah, the ones with all the graphs together.
Yeah.
I guess I can do this in a more effective manner, but. Yes.
Nice. Cool. Thanks. There was a lot there and you went through it. So I just wanted to have a chance to digest that. But yeah, that's really surprising to me. So given that height and cover don't show a response, but annual growth does, do you have any other, or annual growth at least shows a near response, a weak response, let's say. Do you care to like postulate on what's going on there?
Yeah, I think it's interesting. I mentioned this is an observational study compared to, I think Zegenfuss's research, they did actively clip and then Marshall and Billy didn't. And so I think that in context of like, I didn't singularly look at water level and its impacts. I'm thinking that there's other things that could be affecting this. So browse seems to be a more impactful altered disturbance. So there might be that at play. So these results that we're seeing in the relationship between depth and these different growths might also be impacted by browse or something else I'm not considering that leads to kind of this result, because these willows are under all these other conditions at the same time. But I can't really think about, why this was really hard for me because I wanted it to make sense, and this really doesn't quite make sense because it seems like raising water levels, or at least some attribute of the hydrology, should relate to these growth metrics. So again, that could be other parts of it, right? It could be the fluctuation and change in water levels over time since these have been established, or over the year, or just different aspects of water level could be at play as well.
Yeah.
This isn't potentially an issue of like sample size and effect size here.
Yeah, I think that could be the case too. Annual growth definitely has a lot less data collected on it because they took a lot longer. And also because I was limited to where wells were and the depth that wells were. So I couldn't just dig down wells and see, because I wanted everywhere to get to every single water level. So yeah, I think it could be the same thing.
Taryn, one final comment for me is just looking at your data here. If you fit a nonlinear curve instead of a linear response, then if you squint your eyes right, it sort of shakes out with your 100 centimeter depth threshold.
Yeah, that they're growing best under.
Like covers maximized.
Yeah.
Yep. Cover increases and then levels off, height decreases and then levels off, annual growth decreases and then levels off.
Yeah, I think we talked about that early on. That's funny, I forgot about that, but yeah.
And Taryn, we're looking at plot level data, right? On this graph. These aren't plants.
Yes,
These
these
are-
are averaged over each plot, because like I showed you in the photo of what a plot looks like, the center would have one well. So I attributed that water level to all the plants on that plot. So yeah, these are plot level.
And so if we were to look at, because you've collapsed a lot of variance into one point. So if we were to look at all that variance over the depth to water level, what trends would we see? Would the story change? I mean, I know you did this, I just forget what it was.
Yeah, I can't remember either. That's why I'm standing here. I can't remember. There's a lot more variability, right? Because each one of these growth points represents a whole bunch of different plants that were growing differently. And I can't remember if I think it was kind of similar, just like muddled and not straightforward. I can't quite remember. I have to look back. But that is a good point, that I didn't look at individual plants, but compared to water level growth. Good question.
All right, folks. Well, hearing nothing, let's thank Taryn again. Thank you all for